Hello, everyone. My name is Taylor Rudzinski. Thank you for joining us today for Construction Joint Sealants. Our presenter today is Roger Smith. Roger is an architectural specialist that services the Southern California territory. But before I pass it over to him, just a quick few notes. Everyone will be muted for the duration of this presentation. If you have questions, please type your questions into the Q&A box and double check that you are addressing your questions to all panelists. We will be monitoring the Q&A and will be attempting to answer your questions in real time. However, if it does require a lengthier explanation or is a bit more complex, we may hold on to your question until the end of the presentation to answer verbally. We also may need to answer your question through email after the presentation concludes. This is an AIA accredited presentation. Everyone will be receiving certificates sent to the email address you provided to us at registration. If you included your AIA number, we will also be submitting these credits directly to the AIA. Due to the large group in attendance today, I'm asking for everyone's patience. Your certificates and credits will be delivered, but it may take longer than expected, maybe 2 to 3 weeks. And lastly, on the screen, you will see an email address at info@wrmeadows.com. This is our official company email address. If you would like a copy of the presentation or would like to get in touch with your local WR Meadows rep, or have any additional questions for us in the future, please contact us at info@wrmeadows.com and we will get you whatever you may need. At this point, I'll turn it over to Roger.
Thank you, Taylor. I appreciate the introduction. Welcome, everybody. Hope everyone's having a good day. And thank you again for joining us for our presentation on cold applied construction joint sealants. The subtitle is a critical part of the building envelope performance. And I think at times we don't recognize how critical joint sealants may be. They provide great protection in addition to our other systems, and also provide structural protection so that the things that we build and design and construct can perform and reach their expected lifetime. Before I get into the presentation, for those of you who have been with us before, thanks and welcome back. For those of you who have not, a few things about WR Meadows. WR Meadows was founded by the Meadows family in 1926 in Elgin, Illinois. We are still owned and operated by the Meadows family. We have now expanded and have 12 facilities throughout North America, including 3 in Canada, as well as our wholly owned subsidiary, Blue Ridge Fiberboard, who produces sound dampening products and insulation recover board. Here's a quick look at a map that shows you our locations. The yellow designate manufacturing, the gray are warehouse facilities, and you can see we are dispersed throughout the country in order to provide easy access to our products for your projects. As with many companies, WR Meadows started with a product, asphalt expansion joint, but we have since expanded and now manufacture and distribute somewhere north of 380 products throughout the US, North America, and worldwide. We include products in the Division 3 family, concrete accessory products, expansion joint, restoration products, construction liquids, so curing compounds and curing and sealing compounds to protect your concrete, as well as the joint sealants we're going to be talking about today. We also offer a full line of building envelope products, including underslab vapor retarders, air, water, and vapor barriers, and structural waterproofing materials. And then, as I mentioned before, Blue Ridge with their soundproofing and insulation board. Just a quick shout out to another division of WR Meadows, which is our Deco Seal line of products that were developed for the pool industry. And while people think of pools as backyard, there are obviously a considerable number of pools that are built for commercial use, and those products can be used in those applications. One additional thing I wanted to touch base on is our involvement in the industry. WR Meadows has always been proactive in being involved in associations and different entities throughout the building industry. We are a charter member of the Air Barrier Association of America. Obviously, we're involved with continuing education with AIA, because here we are. We're a member of ASTM and sit on several committees and help formulate and decide how to test materials so that as specifiers and architects, you can use these resources to compare and make sure you're getting the products that perform. A couple other ones, International Institute of Building Enclosure Consultants, obviously CSI. So we are active in the industry. We're continually active in the industry, trying to provide better materials and better documents for you to use. As Taylor mentioned, this is an AIA presentation. You will receive credits, either that through an email or perhaps directly to AIA. A couple of the things I want to review before I really get into it. Taylor mentioned that copies of this presentation are available at info@wrmeadows.com. They will also be uploaded to YouTube and available to you. And then as well, one last reminder for those who are coming in and flowing in now. If you have questions, please direct them to the All Panelists section on the Q&A section. I appreciate it. Thank you again for joining us. Let's get started. So today's learning objectives and topics of discussion as far as construction joint sealants, are some terminology, purposes of the sealants, applications, common problems, and then critical success factors, which include joint design and material selection to avoid those common problems that can lead us into some serious issues. A little history on joint sealants. Like so many products that are now being manufactured specifically, people used whatever was available, right? Whether that was pine pitch or wax or tars, those sort of products. As science started to evolve in the 17th century, we saw putties, glazing putties and oil-based putties start to being used. But realistically, as we came into the 1900s, the technology started to develop for the sealants that we currently see today. And if you look at the timeline in the 50s, 60s, 70s, and up into the 90s, some of these technologies are time tested and are still used. Some of them are relatively new when you start to talk about polyethers, STPEs that have been developed. So a wide variety of products, a lot of different technologies, and a long history. So why do we need joint sealants? Well, they do provide that critical line of defense for our structures. And for those of you who have attended previous AIA seminars regarding building envelope products, you have heard the word detail. The devil is in the details, right? Or continuity. Well, many of these joint sealants provide that additional continuity to help prevent water damage, structural steel damage, reinforcing steel damage that can diminish our life cycle, and then also to help prevent mold and mildew. If that moisture gets in our structures and can cause that sort of damage, that can be catastrophic in some cases. As I mentioned, they're a large part of the building enclosure system. Quite frankly, maybe an unsung part, because again, it's easy in my mind to waterproof or protect a sheet of plywood, a sheet of gypboard. It's those details, those joints, those fasteners, those penetrations that these sealants help us protect and build that continuous protection. So they help prevent water infiltration, air infiltration, uncontrolled, cold air into warm, warm air into cold, moisture vapor, sound, and gas or exhaust infiltration. I want to take a few minutes to talk about some terminology that you're going to hear, give you a little bit of an idea of what it means and how it can affect your choice when you're specifying these materials. There's a list of some materials here. Sealants versus caulks. Sealants are the high performance materials that are used in these construction joints. Polyurethanes, silicones, STPEs, polysulfides. These materials have great physical attributes, adhesion, flexibility, weatherability, and that makes them more desirable for our structures. Caulks, for a lack of a better term, are space fillers. And I spent some time in the painting caulk industry in dealing with those products, and they really add a step into the aesthetic issue. So you've got a small gap between a window molding and your drywall. You want to fill that. Doesn't necessarily need a sealant, just needs a good filler. That could be the case in something, maybe some damaged drywall or window areas. Caulks are really space fillers designed to be covered to provide those nice aesthetics that we see. Modulus. Modulus refers to the sealant's ability joint movement, expansion and contraction. Lower modulus sealants better maintain adhesion. They move more, they have more movement capability, and they are generally softer. High modulus, on the other side of the scale, have more limited movement capabilities and can be used for static joints and glazing. But we really live in the middle. Most of our construction joint sealants exhibit a balance of adhesion, expansion, and strength, and are used for most of the applications. So we really deal with medium modulus products. It would be incorrect of me not to point out that no matter what sealant you choose for your project, no matter how good the sealant is, they cannot overcome poor joint design or poor installation and preparation. Shore hardness. Shore hardness represents hardness represents the ability to resist puncture or penetration. Everybody's heard about the high heel penetrating a joint sealant. And generally speaking, sealants with low modulus have lower hardness. Higher modulus sealants have higher hardness. This is not always the case. Now, ASTM 661 is the testing method. You will see that in some of the other documentation. But it's also important to remember that there are two readily accepted scales of shore. There's a shore A scale and a shore D scale. And you want to make sure that you're on the right scale when you're choosing the hardness of your, the rating of the hardness of your product, because the shore D generally represents the harder products, and a shore D of 60 and a shore A of 60 are not the same thing. So make sure when you're looking at these scales, you're on the right scale. Movement capacity. And movement capacity is one of the most critical features, right? The ability to expand and contract with the movement of the joint. We want to make sure we know that our joint sealant matches the movement capacity of the joint it's going to fill. ASTM 719 is the test method. It breaks down the 5 classes of movement. And these are plus or minus. So remember that we're not looking at a plus 25, we're looking at a movement of 25%. But from 12.5 up to a scale of 100 with a 50% recovery, which is what that dual number represents, are the different classes of movement. Again, we live in the medium. Most of the products that you see for application are in the plus or minus 25 or plus or minus 35. Excuse me, the standard specification for elastomeric joint sealants, ASTM C920, has several test methods within it. So you need to understand that you can't just specify 1 or 2 of these. You want to look at overall picture, but they include movement capability, hardness, as we talked about, tack free time, and then adhesion. And I want to take just a second to talk about tack free time, because most of the sealants that are installed are single component and are climate dependent in terms of how fast they cure. So while there's a standard with ASTM C679 for tack free time, the weather at your job site may influence the tack free time and the cure time of your sealants. Some are dependent on humidity, some temperatures make a difference, sometimes it's both. So you have to understand that what you see on the test specification, you may not get on your job site. And then the testing standard, ASTM C920. So here's a line out of ASTM C920-18. Type S, well, what does that mean? That means we're designating the type of sealant, a single component for type S, or if it's type M, multi-component. So it could be a 2-part, which most of the multis are, might be a 3-part, but it is a multi-component. Grade. So in this case, grade NS, non-sag, or grade P, pourable or self-leveling. Class, which describes movement. In this case, 35% movement, could be 50, whatever that number, that tells you what the movement capabilities of the sealant must be. Use, T1, T2, and NT refer to traffic grades. NT designates non-traffic grades. T1 and T2 are 2 different movement levels in the traffic grade materials. And then the use situation. And I've got OMG, right? Oh my God, what does all this mean? No, but they refer to substrates that these materials have been tested for, right? A is aluminum, G is glass, M is mortar, and then O is other materials. So if you're going to pick a sealant, you want to pick one that fits your needs. So we look at a spec, ASTM C920-18, type S, grade NS, class 35, use NT, A, and O, would designate a single component, non-sag, 35% movement sealant for non-traffic use that has been tested for adhesion to aluminum, but not glass or mortar. So this might be a sealant that you're using if you're glazing around aluminum fenestrations. So you know you've got good adhesion to those, but you're not going to glaze with it because it's never been tested for glass. Understand that when you're comparing products, this is your way to make sure that you're getting the right product. If you're looking at something that has a class 25 and your spec is the one that we're looking at above, well, it doesn't really meet the movement that's anticipated with your joint. So make sure that you're comparing your apples and your apples. I'm going to take just a couple other terms that you're going to hear throughout the presentation. Joint interface. All right, that's the sides of the joint where the sealant is adhered. And if you look at the diagram on the bottom, you'll see what we like to call the perfect joint. But you'll see at the sides, that's where the adhesion takes place. Same as in the picture. You can see the adhesion is taking place on the sides. And that interface is important because we want that sealant to adhere properly. There's also a consideration of three-sided adhesion. And it seems simple to say, well, if you look at the picture on the bottom right, I'm going to fill that joint. My sealant is going to adhere to all of those 3 points, and I'm going to be tightly sealed and never have any leaks. The problem is we don't want three-sided adhesion. We want the bottom to be free so that when the substrate, in this case, those two pieces of concrete, expand and contract, the sealant can expand and contract as well. If the sealant adheres at the bottom, and you're seeing a little example of a bond breaker tape there, that black tape, then we can adversely, affect the ability of the sealant to move. So where do we use these products? Well, I could probably just say everywhere and move on, right? Joint sealants are used in all types of construction, all types of locations, infrastructure, airport runways, pathways, sidewalks, highways, critical, right? You can't pour a long expanse of concrete on a highway and expect it to stand up without putting expansion joints in it. Bridges, sidewalks, obviously in commercial buildings. I've mentioned the advent with the building envelopes and being able to seal around penetrations and fenestrations. Expansion joints in our walls in our building structures, our parking structures, plaza decks. I mean, the applications are endless. They're used in all sorts of colleges, schools, prisons. Now, something a little bit different, wastewater and water treatment, where we might be subjected to a submersible application, and there might be a need for a special sealant for that sort of application. So you want to make sure you're getting something that's rated to be in the water, right? Or maybe it's a potable water situation, right? So a water treatment plant where we've got potable water, and you want to make sure the sealant has that NSF 61 or whatever you might need in order to use it with potable water. Obviously huge in tilt-up construction, where we're creating panels and lifting them up and sealing the joints. And then major retail chains, Walmart, Home Depot, those type people. Obviously the warehouse chains, as we're seeing the advent of Amazon and those that are building these 1 million square foot warehouses. How many expansion joints go into 1 million square feet of concrete slab? A lot, right? So obviously used in those situations. What are the substrates? Again, everything. Concrete, brick, block, plywood, stucco, EIFS, changes in plane. Maybe it's concrete to aluminum. Maybe it's wood to concrete, wood to aluminum. All of those different substrates, joint sealants are used. You want to make sure that you're picking products that work with your substrate. And then, of course, the building envelope systems where they're used to seal our penetrations and seal our fenestrations in all those places where we want to maintain continuity of our building envelope systems. Some shots of some applications, changes in material, brick to aluminum, or maybe aluminum to stucco, changes in movement in these products as they expand and contract differently. The sealants serve as that bridge to allow for those products to move independently without losing our watertight and airtight applications. As well as same situation. Here's a change in plane, right? A 90-degree angle where the joint is sealed on the interior corner there. So it doesn't have to be different materials. And then the picture on the right, keep that in your heads as we move along. It's regular expansion in a concrete slab, but notice the positioning of the nozzle and the sealant going in, and I'll talk a little bit more about that later. Excuse me. Also, precast concrete applications. Photograph on the left is a tunnel being built with precast panels, and the joints are being filled with backer rod before the joint sealant is installed. Concrete joints, a picture on the right, a sidewalk to a building sealant that needs to be protected. We want to make sure that that sealant doesn't fail and allow water to get down between those areas. There's a little cut joint in the sidewalk there, which isn't truly an expansion joint, but that could be an expansion joint in the sidewalk that is sealed. And then I mentioned plaza decks and sidewalks. And then here, swimming pools. And again, maybe not your residential pool, but your commercial pool that has an expansion joint in the bottom. There are specialty products and sealants that are designed for those applications. If you're doing that sort of work, you want to make sure that you're using the correct installation methods and the correct sealants. So before we get into choosing our sealants, let's talk about issues that we want to be aware of and things that happen that create problems. And the most commons amongst those are adhesion failure, cohesion failure, and structural failure. Let's take a look at those one by one. So adhesion failure, causes and remedies. Well, causes can be inadequate surface preparation. And that's true of anything when we're trying to apply something that we want to adhere, whether that be paint or a construction adhesive or something like a wallpaper adhesive. Without good surface prep, we're not going to get good success. Contamination, is it clean? Is it free from anything that might adversely affect our sealant? All right. Improper installation, is the product being installed correctly? And possibly in situations, improper priming. So how do we address these? Well, grinding, sandblasting, saw cutting, all sorts of ways to create a good surface, and then cleaning that surface. Maybe that's with a power wash and then an air blast to clean it out. Proper tooling, making sure that we get that good joint interface so that our sealant adheres well to the side of our joint, to the substrate. And proper priming, and we'll talk about that a little bit more, but primers can be finicky. And we want to make sure that we're using them properly, applying them properly to get the effects that we want from them. Cohesive failure, different than adhesive failure, is when the sealant fails, the actual bead of sealant. And you look at the picture on the right, you actually see a couple different instances. One, the wider joint, you see cohesive where the sealant has ripped apart. And then if you look at the joint that runs more north and south, so to speak, you might see that might be cohesive failure. There's also looks like it's starting to pull away from the side, so maybe that's an example of adhesive failure. What causes this? Improper joint design. All right, we've got a joint that's too wide or too deep that we're trying to fill. Improper width to depth ratio. We'll talk about that a little bit. Three-sided adhesion, I mentioned that before. We want the sealant to be able to move in and out with the substrate movement. So obviously we want to go proper joint design, the right sealant for the right joint, and then make sure that it's installed properly. Substrate failure, a little bit different situation where we run into perhaps a substrate that doesn't stand up to the movement. It isn't strong. Maybe the concrete wasn't poured properly. The design was incorrect. Or maybe there's been a washout or something has occurred underneath the slab where the substrate has been able to be damaged on the edges. So how do we avoid this, right? What do we need to do in our specifications, in our selections, to make sure that we avoid these situations? Well, one, I've mentioned it already a couple times, proper joint design, proper substrate preparation, the proper backing materials, and then choosing the material that fits the joint, and then requiring a pull test, right? Making sure that the sealant is performing as designed on the job in real life situations. So, joint design. The joint depth of sealant should be no smaller than 1/4 inch and no greater than 1/2 inch deep. If you're going any deeper than that, you're running into maybe extending your sealant beyond what it's supposed to do. A 2-to-1 width to depth ratio. So if you look at the diagram on the right, the sealant we're looking at is designed to be a 1/4 inch deep, so that joint could accommodate up to 1 inch width. And quite frankly, 1 inch width for a normal joint sealant is about the maximum you want to go. Most joint sealants will not tolerate wider widths, just won't perform. And if you get into wider widths, larger expansion joints, you might want to look at some of the mechanical sealants, mechanical systems to seal your joint. Also consider the hourglass shape. And if you look again at the diagram, on the right-hand side, the sealant has been tooled over the backer rod. You'll see right below the A on the horizontal section, the sealant is convex, which means it's been tooled in, which presses the sealant down into the joint, fills around the backer rod to give us that hourglass shape, and also improves our interface with the sides of the joint and gives us the maximum adhesive qualities that we're looking for. So that hourglass shape gives us the joint design and configuration that we're really looking for. Another thing to consider is the movement and conditions that can occur. And these take a little bit to think about, but a joint sealed at the lowest temperature will always experience compression. And I had trouble with this a little bit in trying to understand this. But knowing that, let's just pick 50 degrees. Your substrates have contracted in the cold, and your sealant is wider than they would be if it was very warm. So when the temperature warms up, you fill the joint with your sealant, the temperature warms, and your substrates expand, which compresses. So if the sealant is installed at low temperature, maybe not always experience compression, but for the bulk of its life, it is going to experience compression. Conversely, if you seal something at the highest temperature, now your substrate is expanded, your joint has shrunk, maybe not visibly, but has shrunk a little bit. Your sealant goes in, the temperature starts to drop, and the substrate starts to contract, and now you're always feeling that extension or expansion of that sealant. And that can be detrimental to the adhesive or the sealant. That's also something to consider. Many joint sealant manufacturers recommend not installing sealants in direct sunlight. There are several reasons for that, but one of them would be that your joint is probably, the substrate is probably expanded, the joint is probably at its smallest, and you're always going to get that expansion pressure on that, which is going to affect your adhesion. So some diagrams of that, looking at a situation where we installed on the left the sealants at probably high temperature. And if you look at the joint design, the sizes are 1 inch wide by 2 inch deep, which is a very detrimental situation. 1 inch by 1 inch, which isn't ideal, but is in real life, a lot of sealants are installed at that 1:1 ratio. And then the preferred ratio of 2 inches, 2 inch wide, or 2 times half the depth. And you look at the strain that's placed on the sealant. In the correct ratio, 32%. In a 2-to-1 or opposite ratio, 94%, 60% more strain. On the other side, if the joint is contracting, right, or your substrate is expanding and putting pressure on this, compressing the sealant, the strain is 12 times as much on the proper depth versus the improper depth. Pressing that joint sealant out of the joint, subjecting it to damage, possibly from traffic, or foot traffic or any sort of thing, where now you really have an issue of the sealant having to fail, because when we open back up, if the sealant's been damaged, it may not continue to fill that joint. Joint design, just a little review. The depth must be sufficient to accept the backing materials. In some cases, an expansion joint might be used with a backing rod. We want to make sure that there's enough room to get our sealant properly installed. Joint should be designed within sealant's movement capability. Well, yeah, that's true, but maybe the sealant should be chosen to meet the joint design capability, movement capability. So that maybe that should be conversely stated. This number and spacing of joints is critical, and that really falls on the engineer who's designing the system and placing those expansion joints. We have to be able to get to the joints. They must be accessible, obviously. And then there has to be sufficient bonding surface for the sealant. And that takes me back to a situation where I was called out on a commercial pool application. Joint sealant had been placed in the expansion joint and had failed and had leaked. So they went in, drained the pool, removed the sealant, let everything dry out, replaced the sealant, and before they could even fill the pool again, the adhesion failed. So I went out to take a look at it. The joint design was not very good. The joint edges were not very good. But the biggest culprit is because the backing materials were not set at the proper level, there was only about 1/8 of an inch on the sides of the joint for the sealant to adhere to. And that, quite frankly, is just not enough. There's not enough interface between the sealant and the substrate, and that was causing the failure. So we took the sealant out again, we recut the joints, reset the backer rod, and gave us that depth of sealant that we needed, so we had that good interface and that good adhesion. So we need to make sure we've got good bonding surface and sufficient bonding surface. Substrate preparation. All right, if you don't prepare for failure. So yes, if it's done properly, we eliminate 90% of all callbacks. It has to be a solid, clean, dry surface to bond these sealants. All right, and that can be accomplished in any number of ways, whether you grind it, you saw cut it, you high pressure wash it, which obviously you need to allow to dry, or just in a situation where maybe it's a small area, you wire brush it, all right, and then clean it. Blow it out with some compressed air, brush it out, make sure that you've got a good surface. If it's not a porous surface like concrete or brick or maybe block, then maybe we just use what's known as the 2-rag method. So we're going to wipe the surface, let's say an aluminum surface, clean, and then follow it with a dry cloth. What we want to make sure is that everything is off of the surface before we apply our sealants, so that we're bonding to the proper area and there are no contaminants. Substrate preparation in all things adhesive is paramount. Backing materials, choosing the right backing materials, sizing them properly, understanding how they perform. There's several different products on the market: closed cell backer rods, a foam material with a surface skin, open cell that does not have the skin, the bicellular, sometimes called soft rod, has specific uses and applications. Expansion joint materials. There are several. Asphalt expansion joint, the original product that W.R. Meadows started with. Excuse me for the promotion there. Asphalt fiber, foam, sponge. They all react differently to our sealants. And again, the idea of the bond breaker tape or backing tape that prevents that 3-sided adhesion. Joint sealants will adhere to asphalt fiber. And that's a bad situation when we get into long-term performance of our joint sealants. Many of you may have heard of snap cap or a plastic cap that installs over the asphalt fiber so that we have a pre-measured depth for our sealant. Well, sealants may stick to that as well. So maybe we have to remember to use our bond breaker tape to prevent that 3-sided adhesion. So why use backer rod? Attain proper wetting of substrate. We want to make sure that we've got a proper surface, right? A proper depth. Control the sealant depth. Remember that 1/2 inch maximum. Prevent that three-sided adhesion. Backer rods generally, sealants generally do not adhere to backer rods. And then make sure that the backer rod is larger than the joint, 25% larger, so that we get a good tight fit. And this works for a couple of things. One is if we just lay a backer rod into a sealant and we don't have a good tight fit, the joint sealant, particularly self-leveling, might just flow around it and flow down and pour into the joint, which one is not a good sealant, two, a waste of money. It also then provides us a good area for a tooling base. If it's tightly fit into the joint, when we press our sealant in to achieve that good interface with the substrate, it will hold its ground, not only to our tooling effort, but to traffic, to give us the support that the sealant needs and the adhesion to the interface. So we've got our joint, we know how to prepare it. How do we decide what joint sealant to use? And there's plenty of them on the market, and they have all different sorts of applications. So we must select a material to handle the anticipated joint movement. Pick the right sealant for the right joint. Does it adhere to my substrate? C920 talks about, whether it's glass, aluminum, mortar, different substrates. Does the joint size allow for sufficient placement of the selected materials? Expansion joints and sealed joints generally have to be wider than 1/4 of an inch in order to get sealant and have it fill and move properly. So just a standard saw cut joint, that you see in floors to allow for control joints doesn't really work well with sealants. Will the product perform under the stated conditions of use? Does it fit my job? Not every sealant works for every application. Is there a history of application successes? Most of the sealants that you see today have been around in the market. The technologies are well time tested. And does the manufacturer provide third-party testing? Right? Have they gone out to somebody and had them test and certify that the sealants fit that ASTM C920 that you're looking at? As I mentioned, there are a ton of different sealants and a ton of different sealants within the sealant chemistry. So you want to make sure that you're selecting the right one for your project. Latexes and acrylics, again, we're really looking at materials that should be referred to as a caulk, probably not a sealant. They don't have the physical properties to match up with the urethanes and silicones and STPEs that are on the market. Relatively low movement, 10 to 12.5%. Used more as a filler to paint over, to create that the good aesthetics we want around in our interior areas and our exterior areas, so that we're not looking at gaps between moldings and within moldings. We can fill them and paint over them. Butyls. Butyls have been around a long time. They have wonderful adhesive properties. They bond to almost anything, including you, if you get them on you. They don't move very well. They're not as good at weathering as some of the other sealants on the market, but they do adhere very well, and you'll see them in areas where there's concerns about adhesion and sealant. My personal experience, quite frankly, is they're hard to work with. They're stringy, they're hard to tool, they want to stick to everything, so it makes them a little more difficult to deal with. And when you're working on the exterior of a building, the last thing you do is to get a bunch of butyl all over it and have to try to remove it. Polysulfides. The first high-performance sealant chemistry has been around for a very long time. Maybe not as good as some of the newer sealants, some of the newer urethanes and silicones. They do have excellent adhesion. They don't recover as well as some of the other sealants. And recovery, that obviously means that when they expand, they may not contract back as well. They can be formulated for good chemical resistance. They're used a lot in the commercial pool and swimming pool industry because they're chlorine resistant and also good for submerged applications. You want to remember that usually they have to be primed for submerged applications and the issues that go along with that, proper priming. STPEs, so we go from the oldest chemistry to maybe the newest chemistry. Polyethers, STPE, MS hybrids are becoming more and more popular in the market because they bond very well. They have good UV resistance. They don't really work well with glass and it can't be used for glazing. Good weathering, not only UV, but to the physical elements. Great, as I mentioned, adhesion, great expansion, contraction. These products are very high solid, very low VOC, and being in Southern California, the VOC capital of the world, that becomes a very desirable trait. And the other thing that we found is they work very well in the building envelope systems, the air barrier and air moisture barrier systems. Excuse me. In part because they have good physical properties, but also they're relatively benign and they're compatible with a wide variety of products. Now that I've said that, don't just go out and pick a polyether or STPE sealant to go with your weather resistive barrier system or your air barrier system. Make sure that you consult the manufacturer, because while they are relatively benign and compatible with most building materials, they may not be with yours. So don't come back to me and say, hey, you told me. No, I told you to check with the manufacturer. Polyurethanes, right? Probably the most widely used sealant in the industry for a number of reasons. While they are generally economical, they also have great physical properties, great expansion, great contraction, good UV resistance, excellent weathering. As the advent of VOC regulations has become more strict, lower VOC formulas are available. They're forgiving. And most of the time when you're walking down the street and you glance down at the sidewalk and the joint is sealed with something, chances are it's polyurethane. They're also paintable. You should consult your manufacturer. In trying to paint over any of these high performance sealants, it's important to understand that these sealants are designed to move. And if you're going to coat them with something, that coating, paint, should also be designed to move. Think of it this way. If I take a sheet of rubber and I paint over it, and then I bend it, and if I've just used a regular standard latex paint, that paint is going to crack when that rubber moves. Or if I expand the sheet, that paint's not going to be able to move with that expansion. And eventually the paint's going to come off of that sealant. So if you're going to paint over these sealants, make sure that you're getting the right material to coat them. Silicone, a newer not necessarily a newer technology, but a very high-end technology, and high-end maybe being the wrong word, high-performance technology. Silicones adhere to a wide variety of substrates. Glass, they're used for glazing and structural glazing. Concrete, wood, all sorts of different things. Generally do not require a primer, although a primer might be recommended. They have excellent UV resistance. And I kind of chuckle. I was involved in the silicone business a while ago, and we all go to Home Depot and we look down the shelf of all these different caulking and sealing materials, and there you see that 50-year warranty type thing. Well, I don't know about that, but I do know that silicones generally have great UV resistance and great weathering capabilities. They can have good chemical resistance. They're good for sealing the perimeter fenestrations. Generally not paintable, not much sticks to silicone. And then another thing to keep in mind is that silicones technologies within silicone can have different applications. For instance, your garden variety Home Depot type silicone cures, and the off-gassing product is acetic acid. Smells like vinegar. If you've gone out some silicone, it smells like vinegar. That product does not stick to vinyl, which created an issue for those vinyl window manufacturers located up in Wisconsin, Anderson, Milgard, and all those guys that are up there, because they needed a sealant that would perform when they were manufacturing these windows and stick to the vinyl. Well, there's a different technology, often referred to as an oxime material, neutral cure silicone, that does stick to the vinyl. So within the silicone family, there are different chemistries that can be used for different applications. So we've included here a usage by type chart. And I just want to stress there's a lot of good information here. If you order the presentation or get a copy of it, or even do a quick screenshot, this can be a nice guide. But remember, it's a guide. right? And it'll give you an idea of where you might want to start to look. For example, on submerged, and you might want to start to look at polysulfides or polyurethanes. But then you might want to talk to your trusted representative, your manufacturer's rep that you work with all the time about what your specific application requires. And I'm, pretty sure that, people in the silicone industry might have issues with this chart. People in the polysulfide industry might have issues with this chart. It depends. And while it is a good guide, please remember to trust your manufacturer's rep. Installation, another part of our designing for success. And while we can't, install the sealant as per manufacturer's recommendations or written instructions, yeah, we want that in our specification. But here's some things that can happen that can create issues with installation. The sealant should be gunned in properly at mid-joint, right? The middle of the joint, so that if it's a self-leveler, the sealant flows out properly. If it's going to be tooled, the sealant is evenly gunned in. And I refer back to that picture that we showed with the nozzle being set in the middle of the joint and the sealant being installed evenly, not only at the width of the joint, but through the length of the joint. That the backing material is installed at the proper depth. And the graphic on the bottom shows the issues that can arise from improper depth. The first part, the front part of that, number 1, shows the proper, right, 1/2 by 1 inch width depth ratio. The second one, the backer rod got pushed too low. We have too much sealant in the joint. We've lost our proper width depth ratio, and we are now subject to those issues, whether that be adhesive failure or cohesive failure that goes along with that. And then the third one, the backer rod didn't get placed properly. It was too shallow. We don't have enough sealant in the joint to perform. It doesn't develop the cohesive strength that we need and can end up tearing. I've got a quick little shot up in the top right of a tool designed to set the backer rod at the proper depth. And something as simple as that can help prevent some of those issues. Priming. Obviously, priming can help get a better bond. Paint, waterproofing, all sorts of different things. Primers can help with the bond. But it's not a substitute for good preparation. We still need a properly prepared, clean joint ready to accept our sealant. Generally used on horizontal applications, almost always used in submerged situations. You need to understand the usage of the primer, because sometimes if you leave a primer in for too long, it loses its priming ability, and in some cases may even flip around and become a bond breaker and prevent the sealant from adhering. So if it says all prime surfaces must be sealed within, or material applied within 24 hours, well, you either have to fill that joint today, or you may have to reprime tomorrow. If you want to make sure that you're priming both sides of the joint, following the instructions of the primer, and then as the photograph provides evidence, protect the substrate, because some of these primers can stain our substrates, and the last thing you want to do is apply a primer and damage the surface that you're trying to seal. Obviously the expense involved and the removal of the primer and perhaps the substrate could become problematic. And then an adhesion test. Included a note that we want to test on the site for adhesion. The job site pull test is relatively simple to do. It takes a little bit of art and a little bit of experience, but we want to adhere the sealant to the substrate, or I'm sorry, install the sealant on the substrate, let it cure, because these sealants, and cure is important because it's not just dry. It has to be allowed time to develop its full adhesive quality. And then we're going to pull the sealant back. And as the diagram on the right shows you, we are not looking for, we are looking for cohesive failure. We want the sealant to rip. Remember, it's an adhesion test, not a cohesion test. If the sealant pulls off the substrate, we've got a problem. And we're going to have to re-examine the sealant that we chose, the preparation of the joint. But this can do a lot to prevent long-term problems on our projects. Master Format Section 079213, guide spec for elastomeric joint sealants or specification for elastomeric joint sealants. Some sections to consider: 1.03 to reference our ASTM standards, 661, different sorts of things. Quality assurance. Does the manufacturer have experience? Does the installer have experience? All right. Materials. This is where our C920 comes in. Do we do a performance specification and you have to meet this alone? You want to make sure that you're getting a silicone because you want silicone, because just C920 may not tell you that you want a silicone. It might, obviously would allow for a urethane. Accessories. Do we want a primer? Do we want a baccarat, a specific material, so that the installation goes properly? And then the all-important joint preparation in execution, 3.02. Want to make sure that we define the preparation. And oftentimes that might only be joints should be prepared as per manufacturer's written specifications or written instructions, but we want to make sure that we account for the joint being properly prepared for our installation. So in summary, joint sealants provide critical service to our structure's performance and longevity. They absolutely do. And probably underappreciated, right? They're very, very critical. There's significant performance differences between sealant and caulk: expansion, contraction, adhesion. Caulks are generally considered fillers. Proper joint sealant design, preparation, and installation will lead to a successful application, right? There's nothing better than proper preparation. There are many types of joint sealants. Select the type that is best for your project. Not everything works for everything. And then lastly, you have now graduated into the situation where you can, when walking down the sidewalk, annoy your friends or your significant other as you pass over, like many joint sealant manufacturer representatives do, different sealants, and notice that they may have failed and why they failed and how they failed. And you can explain that to your friends, and you can really annoy them with that type of information. That concludes our AIA portion of the presentation. I hope you've enjoyed it. A couple other things before we get into the questions. If you're looking for more information, WR Meadows website, all right, www.wrmeadows.com. We have, along with data sheets and SDS sheets, guide specs, CAD details, BIM models, training videos, project profiles where you can see these products and where they've been installed. The info at wrmeadows.com. If you're looking for the presentation or you're looking for a sales rep in your area to contact you, let us know and we will have that person come out and get a hold of you. So many different things. Before we get all into the questions, and on the outside of the AIA portion, when you receive your certificate, you're going to receive this document, and it's a guide set up by Master Format to show you what products WR Meadows have that will work in your Division 7 applications. And obviously, if you take a look at this, we've got a lot of them. I think it's an excellent guide, handy to have around, whether you print it and keep it in your desk, like the old-fashioned guys like me do, or you keep it on your computer. It's a very good, quick reference. So with that, let me thank you again for your attendance. And Taylor and Patrick, what do we got for questions?
Thank you, Roger. Excellent job. Thank you, everybody, for attending as well. Like Roger mentioned, we do now have a couple of minutes to address your questions. Moving into the first one, why do you call the joint in concrete an expansion joint? Concrete shrinks and masonry expands. So wouldn't the proper term be contraction joint or movement joint?
Well, I don't know that I want to get into semantics. I think I'm using more of just an accepted term. So I'm not going to argue. Yes, it could be, but I think if you're looking at concrete, I guess I'm not going to argue with the terminology. I just think the generally accepted term of an expansion joint is well regarded.
Roger, we have another question. Is using backer rods considered three-sided adhesion?
Well, it depends on the backer rod, and most sealants do not stick to typical backer rods. But that would depend on your sealant and your backer rod. The tendency of a sealant to possibly stick to an open cell backer rod might be higher, but generally speaking, the cool rod type products that are skinned prevent adhesion, which then prevents that three-sided adhesion. But it would be, sealant and product and backer rod dependent, quite frankly.
Great, moving into our next question. What product would you recommend for green concrete?
I'm open to help with this one. Generally speaking, we don't want any moisture. I think I'm going to have to say, give me a chance to research that, and I'll get back to you.
Roger, here's another question that says STPE question mark. I assume they're looking for a definition of STPE.
Silane terminated polyether is what that acronym, I believe what that acronym stands for. It is depending on how you look at it, some people consider it a modified polyurethane. Others might consider it a modified silicone. There's a little bit of discussion about that, but basically it changes the chemical makeup. If you look on the chain of the molecules, the termination is a little bit different. So the material is a little bit different than a typical polyurethane, but that's what STPE stands for.
Thanks, Roger. And moving into our next question, do you have any fire stop sealants?
WR Meadows is not involved in the fire stop sealant industry right now. Who knows what the future holds, but no, we do not.
Roger, here's another question that just came in. Will joints always fail at some point?
That's
a good question.
Yeah, I guess really when you consider it, none of these products are unlimited lifespan, particularly when you consider what they're being asked to do, exposure to elements, exposure to traffic, exposure to movement, freeze thaw in certain areas. I don't have that issue here in Los Angeles, but yeah, they are, in my mind, to some degree, a maintenance item, particularly those sealants that are left out in the elements and probably will need to be maintained at some point in time. Now, if you look at sealants that are used, let's say, behind facades in the building envelope industry, where they're not as subjected to the elements, you're probably going to get longer life. But to have a joint sealant, joint last forever, I think that might be asking a lot.
Moving into our next, can concrete sealers interfere with adhesion?
Absolutely. Depending on the makeup of the concrete sealer, the potential for creating a surface that doesn't adhere well. And I'm not saying that they all do, and penetrating sealers in particular generally do not, but there's always potential that if you get the sealer down onto the interface of the sealant joint, you could create a situation, particularly with some of the higher gloss materials, where we've affected adhesion capabilities quite a bit.
Roger, here's our next question. What is the typical lifespan for the different sealant types?
Well, if you promise not to take me to task on this, if you're looking at the caulking materials, the latex and acrylics, you're probably looking at something that should be maintained every 3 to 4 years, depending on your environment and your application. You know, the urethanes, the polysulfides can last much longer. But again, in significant movement issues and significant climate issues, you know, maybe you're looking at closer to, you know, I guess 7 to 10 years. You know, silicones probably last the longest and have been known to perform for a very long time. I don't know that I really want to put a time value on that because each application is different. Each area is different. Like I mentioned before, freeze thaw and those sort of environments can be more detrimental. Or, you know, conversely, let's take it out into the desert and get that 120 degrees and that hot sun beating down on it. That's probably not good for the life of it either. So I think there's too many variables to just say, yeah, they're going to last this long.
We have now approached the 1 o'clock hour, so this will be our last question for today's presentation. Are joint sealants needed in exterior sidewalks?
Well, that depends. Do you want your sidewalk to last? Because if you take a 4 foot wide by 100 foot long length of concrete and don't put a joint in it, it's going to crack. Now, that's what that joint is there for, to take up the movement of the concrete so that it doesn't crack in the field, so to speak. Well, that's the last thing we want to do is have a cracked sidewalk. What we're trying to do is prevent water from infiltrating in and deteriorating the reinforcing steel and causing an earlier failure than is needed. So yeah, we definitely wanted to make sure that we get joint expansion joints and joint sealants in our sidewalks to allow for that movement and to prevent the concrete from cracking.
Thanks so much, Roger. If we were unable to answer your questions in today's presentation, we will end up reaching out to you through email to answer all questions. In closing, we appreciate your attendance in today's presentation. Thank you so much and take care.
Thank you, everyone.